Let's look at problem 21 here. With 21, we have a problem that came up on the quiz. This is one of those ones that does not have a different kinetic and thermodynamic product. On this one, we're not going to get the 1,4 product. In other words, only the 1,2 product. But that still means, though, that they can be kinetic and thermodynamic based on the conditions. This is just going to produce the same product. So let me do the mechanism for that. I'm going to turn this around too. So here, this is the one we went over in class, and I added a ring onto it. When this reacts with the HCl, doesn't matter what temperature it is, it's going to form the most stable carbocation here. And again, position 2 or 3 are going to be the ones to get the carbocation. It never reacts against resonance here to produce something more stable. In other words, all we're looking for is the most stable carbocation. So that will react. We get this carbocation here. That's on a secondary carbon, but is also at the same time on this tertiary right here. Here's the resonance for that. This resonance will also show that a double bond here is not quite as stable. Here it's not as stable because we only have 1, 2 alkyl groups that are on this double bond here, rather than 1, 2, 3. Right there. Oops, do you see that? 1, 2, 3. Okay, so this one's going to be tri-substituted. Right here, this is 1, 2. That one's going to be di-substituted. This is the more stable double bond. That's the point I'm trying to hammer across. If we're at thermodynamic conditions, the most stable double bond is the one product that results. Here you can see if this reacted here, that's the 1 position. And the 2 position then would be right next to it, right here where the positive charge is. So we get our product then, it looks like this. Which it technically is the 1 and the 2 product. So we only get a 1,2 product regardless of temperature with this one. Excuse me, 1 and 2 product is the one that we get from that. And it's the only one. Okay, moving on. Number 22 here is a classification one. And this one here is the structure of caffeine. A little bit confusing because we have double bonds in there. Here we count these 2 lone pairs because they are right beside sp2 atoms, carbons. So we do count those. And here we have 2, 4, 6, Huckel's rule. These carbonyls are necessary to have a fully conjugated system, sp2 hybridized. And you can see if I did the resonance for this on both of these nitrogens right here, the molecule will look like this. Okay. So here we can see we got 2, 4, 6 to Huckel's rule, and that looks more like a benzene type ring now. So we need to count up all the electrons though, because this is also an aromatic ring over here. So we have 6, and then we count these over here, 8, and then there's a lone pair right here. This is like a imidazole ring over here, but that makes 10, and there is the Huckel's rule right there. Okay, the next one is another reaction, thermodynamic conditions. This molecule right here is a little more straightforward. So let me do the mechanism for that, 23. Okay. Inside carbons, we'll get the carbocation. We have a choice between this one and this one. We are reacting with Cl2 here in this case. So this is a little bit different. Cl2 will react with the most substituted double bond here. So here's the mechanism for Cl2 reacting right here. This one will form this chloronium ion here at the start, but it will swing open like that because it is resonance stabilized, and we have just as stable of a carbocation right here. Now, since this is heated, 45 degrees, the double bond will move over like that, and we get the resonance. Form like that, and now we react this position because this is a di-substituted double bond, and this is a mono-substituted double bond there. These are heated conditions again, so most stable double bond should form in this one. This is the same as the others. So there we match up that one to letter D over here. Number 24, we have a determination of an aromatic ring. In this one, we have a carbocation. The carbocation is right here. It's not shown, but there is a hydrogen there. We got 1, 2, 3 electron groups there. That means we have sp2 hybridization with 3 electron groups. So we needed that carbocation to create a fully conjugated system. Now, one of these lone pairs is going to come down with the resonance, and it's helpful to draw the resonance to see that we have something very similar to what looks like a benzene ring with 3 alternating double bonds there. Okay, so we got 2, 4, 6 pi electrons there. That is aromatic with 6 pi electrons. That follows Huckel's rule.